Hello everyone, welcome to Math 115, College Algebra. So in this section, we're going to talk about linear functions. So in Chapter 3, we talked about functions in general. Now we're going to talk about some specific types of functions. So we're going to begin with linear functions. Now we've kind of already discussed linear functions without really calling them functions back in Chapter 2. So if you remember, a linear equation, right, has the form y, or at least this is one way to write it, y equals mx plus b. So we call this a linear equation. But because for each input x is associated with exactly one output y, this is also a function, right? So if we replace the y by f of x, we can write it basically as a function. So basically we're just replacing y by f of x. Since this is a function. Okay, and that's what I did right here, right? So linear functions are basically going to have the form f of x equals mx plus b, where the slope m here is constant, right? It represents the rate of change. And then b is, you can think of b as the initial or starting value. It's basically the value of the function when x is equal to 0. Okay, and we know from earlier, from chapter 2, that the ordered pair 0 comma b represents the y-intercept when we graph this linear function. Okay, so again, a lot of these things will be reviewed, which is good because you've seen some of the stuff before, but we're just going to emphasize the fact that now it's really a function. All right. There's several ways of representing functions. You can represent them basically as a sentence, right, in word form. You can represent them in function notation. You could represent them as a table, so tabular form, or as a graph in graphical form. So for this example, let's look at all the 4 different ways of representing this function. So first of all, the word form is given here, right? So you're told the train's distance from the station is a function of the time during which the train moves at a constant speed plus its original distance from the station. Express this function in the other forms. Okay, so first of all, this is the word form, right? We're just describing the function in words as sentences. All right, what about function notational form? Well, first of all, we need to come up with some variables that represent different things like the distance from the station, the time, etc., etc. So let's let t represent the time, right? And it's in, I think it's in hours. Yeah, the time in hours in this case. I'm going to say x is going to be the distance from the platform. And this will be, say, let's do miles. The speed, remember we're told it's a constant speed. Let's just call it s. So s is the constant speed. And it has units of distance per time, right? It's miles per hour in our case. So this is our constant speed. And it has units of miles per hour. It's basically going to be our slope. And then the original distance from the platform where the train starts, let's call that D. So this is the original distance from platform, and that is also in miles, right? This is in miles. Okay, so I can write this equation as a linear function, right? My output, which is x, right, the distance from the platform, is equal to the speed times the time plus the original distance. Okay, so t is sort of like my input, and x is my output. So basically, we can say x is a function of t. So x is equal to ft, which is equal to st plus d. Right? So really, in this case, this is our slope, right? The speed is our slope. And the d is our initial value, or you can think of it as the y-intercept when we graph it. I'll write both. So I'll say it's the initial starting value. It's the value of the distance of the train from the platform when the time is equal to 0. Okay? By the way, sometimes engineers and physicists do this. Instead of this notation, they kind of shorten this, and they'll say x is a function of t. Just another notation you could use to represent the fact that it's a function. Okay. So that was function notation form, right? So function notation. What about tabular form? Let's do this as a table. So as a table, we're going to have to come up with some specific values here. Let's say, so I'll say tabular form. Let's say the speed s is 40 miles per hour. And let's say the starting distance is 5 miles from the station. Okay, so if I form a table here, my input is the time t, right, in hours. And my output is going to be x, which is the same thing as f of t, right? And that'll be in miles. So I'll just pick some times. Let's say 0, 1, 2, 3. So those are all in hours. And to find the corresponding distance that the train is from the platform, I just plug into the function, right? Basically, I'm finding f of 0 here. So that's going to be 40, right? S times t plus d. And in this case, that's 5 miles. Then I want f of 1. So that's going to be 40 times 1 plus 5. So it's going to be 45 miles away after 1 hour. Then I want f of 2. So it's 40 times 2 plus 5. So what is that? 80 plus 5? 85 miles away. And then f of 3 will be 40 times 3 plus 5. So 125. So after 3 hours, it's 125 miles away from the station. Right? At 0 hours, it starts at 5 miles away. So you can see here, that's kind of like our y-intercept, right? When the time is 0, the distance from the platform is 5 miles. After 1 hour, it's 45, and so on. Okay, so that would be tabular form. The data is given in a table. And then graphical form is basically plotting this, right, and then drawing a smooth curve through all the data points. So let me do the graph over here to the right of this. Move this a little bit over. All right, since we're only talking about positive time, I really just need to focus on the first quadrant. Okay, so this is our time in hours, and this is our distance from the station in miles, right? This is like our x, this is like our t. So when the time is 0, what is the distance? It's at 5, right? So let's say 5 is like right here. When the time is 1, the distance is 45. Let's say it's right here. So this is, say, 5. This is 45. When it's at 2, it's 85. Let's say that's like right here. So at 0, it's 5. At 1, it's 45. At 2, it's 85. And then if I draw a smooth curve through that, notice it's going to be a line, right? It's going to be linear because this is a linear function. So it's going to do something like this, and it's going to keep going, right? At least, I mean, the train may stop at 3, but you could keep going, right? Let's say it traveled for a few more hours. That line would just keep going. Okay, so that would be the graphical form of that linear function. All right, so it has, you could do word form, you could do functional notation form, you could do tabular form, or you could have graphical form. Okay, let me remind you about some things that we talked about in chapter 2 about linear equations that will apply for linear functions as well. So remember we talked about the slope of a line, and there's several different possibilities, right? Actually, there's 4 different possibilities in this case. So one possibility is the graph looks like this. So that would be an example where the slope, since I'm reading from left to right and it's going up, is greater than 0. Okay, the slope could be, the line could be doing this. In this case, the slope would be less than 0, right? So if I'm reading left to right, it's going down. The line could look like this, right? It could be completely flat, right? Which is a constant function. In that case, since there is no slope, remember the slope measures the steepness of the line. Since there's no steepness, then we say the slope is 0. Or the last possibility is it could be straight up and down, right? A vertical line. In that case, the slope is undefined, right? Remember the slope doesn't exist in that case. Basically because if you try to calculate it, you're dividing by 0, right? Some people will say it's infinitely steep. The slope is infinite, but the best answer is it's undefined. Okay, so those are the 4 possibilities. Slope could be positive, negative, 0, or undefined. All right, let's look at some examples with this now. So if f of x is a linear function, and 2, 3, and 0, 4 are points on the line, find the slope. Is the function increasing, decreasing, or constant? And how do you know? Okay, so basically, again, we already know how to do this, right, from chapter 2. Let's look at those 2 points. We're going to label them, right? So the first point I will label x1, y1. And the second point I will label x2, y2. So to calculate the slope, remember it's the change in the output. So it's y2 minus y1 over the change in the input, x2 minus x1. So this would be 4 minus 3 over 0 minus 2. So that will be, I guess, negative, let's say this will be 1 over negative 2, so negative 1/2. Okay, so since the slope is less than 0, that means the function f is decreasing. Right? If it's less than 0, the line's going to look something like that, right? So the function is decreasing over time. Okay, and how do we know that? Again, because the slope was negative. Okay, here's another example with slope. In this example 3, you're told the population of a small town increases from 1442 to 1868 between the years 2019 and 2022. Find the change in the population per year. So when we're looking for a rate of change, right, if it's a constant rate of change, that is essentially the slope. Okay, so the way to think about this is I just basically need to calculate the slope. But let me write down the ordered pairs here. So the first is 2019 is the time, right? Actually, let me call that T1 for the year, right? That's the time or the year. And then the population at that year is 1442. I'll call this like P1 for population 1. And then for the year 2022, I'll call that T2. What was the population? It was 1868. So that was P2. So the rate of change in the population is really just the slope. And how do I calculate the slope? Well, it's going to be the change in output, right? So the change in population, P2 minus P1, over the change in time, T2 minus T1. So this will be 1868 minus 1442 over 2022 minus 2019. This is equal to 426 over 3. And then you can simplify that to 142. You can think of it as 142 over 1 if you want. And then what are the units? Well, the change in the P is a change in the number of people, right? So this is like people per, and then the change in time is a change in the year. So this slope, this average rate of change, has units of people per year, right? So basically the population is, since it's positive, the population is increasing. I'll write that here. So population is increasing by 142 people per year. That's how to interpret it. Okay, and we'll do more applied problems. A few more in this section and definitely in the next section in 4.2. Okay, equations of linear functions. Again, we've already done this back in chapter 2, but now we're just going to use more functional notation. So example 4, if f is a linear function with f of 3 equals negative 2 and f of 8 equals 1, find an equation for f of x in the slope-intercept form. Okay, so when they give you f of 3 equals negative 2, remember 3 is the input, negative 2 is the output, right? So really this corresponds to the ordered pair 3 comma negative 2. So 3 is kind of like our x1, negative 2 is like our y1. Okay, and then same thing for the second, so f of 8 is equal to 1. So this corresponds to the point 8 comma 1. So you can think of 8 as our x2, right, our second input, and 1 is our second output, y2. So how do I find the equation of a line? Well, I first need to calculate the slope, right? I'm going to need the slope. So the slope will be y2 minus y1 over x2 minus x1. Or you could also write this as, remember this means the same thing, f of x2 minus f of x1 over x2 minus x1. And what is that? Well, that's really f of 8 minus f of 3 over 8 minus 3. Right, and we know f of 8 is 1, f of 3 is negative 2, and then 8 minus 3 is 5. So it looks like this is going to be 3/5. Okay, all these different notations they all mean the same thing, right? So the slope is the change in output, y2 minus y1, over the change in input, x2 minus x1. But y2 minus y1 is the same as f of x2 minus f of x1, right, over x2 minus x1. And then f of x2 in this case is, so that's f of 8, right, minus f of x1, f of 3 over 8 minus 3. But then f of 8 equals 1 minus f of 3 is negative 2 over 8 minus 3 is 5. And then 1 minus negative 2 is positive 3, so it's 3/5. So that would be the slope. Okay, then how do I find the equation? Well, you could go directly to the slope-intercept form, right, and find b, or you could use the point-slope form and then just rearrange it at the end to put it in the the slope-intercept form. So I don't know. Let's do the point-slope form. So I'm going to make a little bit more room over here. I'm going to have y minus y1 equals m times x minus x1, right? So in this case, I have y minus y1 equals, we know the slope is 3/5, x minus x1. So I need to use a point. I can either use, I could use this point, right, 3, negative 2, or I could use this point, 8, 1. It doesn't matter. Let me just use the 8, 1. So I have y minus y1, which is 1, equals 3/5 x minus x1, which is 8. And then if I distribute the 3/5, this is going to be 3/5 x, I guess minus 24/5. And then to get it in the slope-intercept form, I need to solve for y, so I'm going to add 1 to both sides. So I'm going to have y equals 3/5 x. What's negative 24/5 plus 1? Well, that's the same as negative 24/5 plus 5/5, right? I'll do it up here. So negative 24/5 plus 1 is the same as negative 24/5. I want the same denominator, so I can rewrite the 1 as 5/5, and that's going to be negative 19/5, right? So this is minus 19/5. So that's our answer, but we want it actually in function notation. So instead of y, I'm going to put f of x. Okay, so again, nothing new. You've done this before. We're just using function notation now for that linear equation. Okay, next example. So this one is going to be sort of a word problem, right? An application. It says, suppose Sabrina starts a company in which she incurs a fixed cost of $1,250 per month for the overhead, which includes office rent. Her production costs are $37.50 per item. Write a linear function C, where C of x is the cost for x items produced in a given month. Okay, so first of all, let's figure out what these things represent here. So the $1,250 here, this is like the fixed cost. This is the cost when 0 items are produced, right? So this is basically the y-intercept. In particular, it's going to be the b, right? It's the cost when there are 0 items produced. It's like the upfront cost, okay? All right, what is the slope? Well, here, if you notice, right, if you read this carefully, this is $37.5 per one item, right? So it has units, right? It's like a rate of change. So the slope here is $37.50 per one item. No one writes the one, but it's really per one item, right? That is the slope. Okay, so once you recognize that, then we can just write out the linear function directly, right? We know that c of x is going to have the form mx plus b. But we know that the m is 3750. And we know that the b was 1250. So that is my linear function, right? That represents the cost. It'll be the total costs for X items that are produced in a given month. Okay, and notice it makes sense, right? If zero items are produced in a month, if you plug in 0 for X, what do you get for C? Well, you're just going to get 1250, right? Because that's like the initial cost when 0 items are produced. That's what you need up front. Then if 1 item was produced per month, then it'd be 3750 times 1, or 37.5 times 1 plus 1250. Add those together. That would be the cost per month if 1 item was produced, right? It'd be C of 1, and so on and so forth. Okay. Graphing. So let's review graphing. Again, we've done some of this before, but so this question says, using 2 points, or at least 2 points, plot and connect the dots or write the function in slope-intercept form and use the y-intercept and slope to sketch the graph. Okay. All right, that's probably, in this first example, that's probably the easiest way, right? This already has the form f of x equals 1/3 x minus 2, right? Or if you want, you can write it as y. We can go back to the equation form. Right? This is like the function. This is the function form. This is the equation form. They're really the same thing. And in this case, it already has the slope-intercept form, right? We can interpret this. M must be 1/3, and then B must be -2, which means the y-intercept is 0, -2. So if I want to graph this, I definitely know 1 point, right? The y-intercept right there. And then the slope tells me that if I move 1 in the y direction, +1, this is like my rise, and then +3 in the x direction is like my run, that'll give me the next point on the graph, right? So if I start here, I know 1 point, right? I definitely know the y-intercept. If I move up 1 and then over 1, 2, 3, that must be another point, right? Then up 1, 1, 2, 3, that must be another point, and so on. So up 1 over 3, that'll be right here, this point, and then up 1 over 3, that'll be this point. And now I can graph the line by drawing a smooth line through all those points. So it'll look something like this. Okay. Another example with this. This is very similar. So this is also in the slope-intercept form, right? You just have to rearrange the values here. So I can write this, because I want the mx first, right? So I want to write the negative 2x first, and then the constant plus 4. So that has the form y equals mx plus b, where m in this case is negative 2, and then the b is positive 4, which means the y-intercept is 0, comma b, right? 0, comma 4. Okay, and for the slope, you can think of this as negative 2 over 1. So negative 2 is the rise, and 1 is the run. So if we try to graph this, so this is x, this is f of x. Let's see, we definitely know the y-intercept, right? So 0, 4, that point is right here. And then if the slope is negative 2, that means if I move down 2, right? So the rise is negative 2, so I move down 2, and then the run is positive 1 over 1, that should be the next point, right? And then down 2 over 1, that'll be the next point. So down 2 over 1, I should have a point here that lies on the line. Down 2 over 1, a point here that lies on the line. Down 2 over 1, a point lies here. And then if I draw a smooth line through those, that'll be the graph. So something like that. Okay. So we just drew graphs, right, given the function. Let's write the equation or the function given the graph, right? So let's go backwards. So basically we just have to interpret the graph. So in this question, I want to write the equation of each line shown in the graph. So there's 4 graphs, right, 4 lines, so I want to write 4 equations. Okay, so let's look at each of these carefully. So I'll start with 1. Let me do this in black here. Start with 1. All right, so what do I know about line 1 here? That's the orange one here. Well, definitely the y-intercept is 0, 3, right? Which means the b is 3. And then I could figure out the slope by thinking about the rise over run. So let me pick some point. Actually, it's kind of hard to use this one. Because I want to move to the right. You don't have to do it this way, but let me pick this point right here. So to get back on the line, which is say right here, what do I need to do? I need to move up 1, 2, 3, 4, and then let's see. Yeah, so let's look at it again. So I need to go, if I start here, I need to go 1, 2, 3, 4. So rise is 4 and over 2, and I'm back on the line. Or you could say 1, 2, 3, 4, 5, 6, and then over 3, right? And then you're back on the line. So in either case, to figure out the slope, I'm thinking about the rise over run. I'll use the fact that I had to move up 6 and then over 3 to get back on the line. So that means my slope must have been 2, right? So therefore, the equation is y equals mx plus b. So in this case, it's y is equal to 2x plus 3. And if I want it in functional notation, I write it as f of x equals 2x plus 3. Okay, so that's for graph 1. All right, what about 2? Let's see, where's 2? So 2 is the blue one here, right? So the y-intercept is the same. is again 0, 3, which means b is 3. And then for the slope, I'm going to start here and go to here, okay? So I need to move 1, 2, up 3, and then 1, 2, 3, 4, 5, 6, right, to get back on the line again. So my rise is a positive 3, my run is a positive 6. So my slope in this case is going to be a half. So therefore, the equation is y equals mx plus b. So y equals a half x plus 3. And then as a function, I can just write as f of x equals a half x plus 3. So that would be the equation of the second line, right? The blue line. Okay, what about the third? All right, so the third line is this one, right? This greenish color. In this case, it looks like the y-intercept is 0, negative 3. Which means that the b is a negative 3. The slope, which is rise over run. Let's see. Again, I like, you could actually move to the left and down, right? That will also work, but, or down and to the left. But let me always move to the right. So I'm going to pick this point, the y-intercept, and then this point. It definitely goes to this point 2, 1, right? So if I start here, what do I need to do? I need to go up 4, right? 1, 2, 3, 4, and over 2. So my rise is a positive 4. And my run is a positive 2. So that means the slope is again 2. So now I can write the equation, right? It's y is equal to 2x, and then b is negative 3 now, right? Plus a negative 3, I can write minus 3. Or in function notation, f of x equals 2x minus 3. Okay, and then finally, the fourth line, that one is, let's see, that's this dark blue one, right? Again, it looks like the y-intercept is 0, 3. Which tells us that b is equal to 3. And the slope is rise over run. So for this one, let's start here at the y-intercept and go down to, where does it definitely go through? It definitely passes through 3, negative 3, right? So how do I get there? Well, I need to move first down 6 and then over a positive 3, right? So my rise is a negative 6 and my run is a positive 3, and that's going to give me a negative 2 for the slope. And now I can write the equation, right? Because I know m. Once you know m and b, then you're done, right? You can write the equation. So in this case, slope is negative 2, so it's negative 2x, and then plus a positive 3. So that would be the function f of x equals negative 2x plus 3. Okay, so not too bad. All right, and then a little bit more. Again, we talked about this in chapter 2. Let's just review a little bit about parallel and perpendicular lines. Okay, so remember that two lines are parallel. And what does that mean? It means that they never intersect, right? They never cross. They go on forever and never cross. If what's true? If their slopes are equal, and technically their y-intercepts must be different, right? Because otherwise they could be exactly the same line, right? If they have the same slope and same y-intercept, they'll be the same line. And then how do we know that two lines are perpendicular? Well, first of all, what does it mean to be perpendicular? Remember, they're going to intersect in such a way that they meet at a right angle. So this would be like a right angle here, 90-degree angle. And the test for two lines being perpendicular is that if I take the product of the slopes, I end up with -1, right? Or another way of writing it is saying that the second slope equals -1 over the first slope. It's negative reciprocal of the first slope. Okay. All right, so in example 9, we're given several linear functions, right? F of x, g of x, and h of x are all linear functions. Oh, no, 4 of them, and also j of x. Which ones are parallel? Which ones are perpendicular? Well, if you just look at these, remember, to be parallel, they have to have the same slope, right? So if we look at these, it looks like f and j are going to be the ones that are parallel, right? Because f of x is equal to 2x plus 3. J of x is equal to 2x minus 6. So in this case, m1 is 2. In this case, m2 is also 2. So the slopes are the same, right? Same slope. But b1 is 3 and b2 is -6. So different y-intercepts. Therefore, f and j are parallel. Okay, and then which ones are perpendicular? Well, we have to find the line such that when we multiply the slopes, we get -1, right? It looks like it's going to be the half and a -2, but let me double check that. So here, I'll write this down. So g of x is 1/2 x minus 4. So that says that the slope here, I'll call it m1, is a half. And then h of x is -2x plus 2. So in this case, m2 is -2. Now, if I multiply those, what do I get? So I have a half times -2. You can think it was -2 or 1. Well, the 2's cancel, right? And I have 1 times -1 over 1 times 1. There's just a 1 here now. And that's equal to -1. So this is telling us that G and H are perpendicular. Okay, so G and H are perpendicular. Okay, and then again, we're going to do a few more examples in function notation of what we already talked about in chapter 2. Like now finding equations for lines that are parallel to a given line or perpendicular to a given line. Okay, so let's look at example 10 here. Given h of x is 2x minus 4, write an equation for the line through the point 1, 3 that is parallel to h of x. Okay, so for the given line, we know the slope, right? It's in the form mx plus b, so I can just pick out that slope. That is my m1, so m1 is equal to 2. Let's call it m1. And then for the new line, that's going to be parallel to that h of x, I want my new slope, m2, to equal m1, right? So I also want it to be 2 in order for it to be parallel. Right, so the new line is going to have a slope m2 of 2, and it's going to pass through the point 1, 3. Okay, so we can find this line just by using the point slope form or the slope intercept form. It doesn't really matter. Let me call this x1, y1. Let me just use the point slope form. So I have y minus y1 equals m times x minus x1. So y minus 3 is equal to we want our m2, right, which is 2 times x minus 1. I'll distribute the 2 here. Usually you want your final answer to be in the slope-intercept form, right? So 2 times x is 2x, 2 times negative 1 is negative 2, and then I'll solve it for y. I'll bring over to 3. So it looks like y is equal to 2x plus 1, right? So that's our answer. If we want it in function notation, we could just write it as f of x equals 2x plus 1. Okay, so this function, right, which represents that line, is going to be parallel to this line, to the h of x line, except this one passes through the point 1, 3, right? We can check that. If we plug in 1 for x here, 2 times 1 is 2, plus 1 is 3, right? We can output, if the input is 1, the output is 3. All right, and then let's do one more where the new line is going to be perpendicular to the original line. Okay, so in this case, we're told a line passes through the points -2, -15, and 2, -3. Find an equation of a perpendicular line. So we want a new line that's perpendicular to this given line that passes through the point 6, 4. All right, so what I need to do first is I need to find the slope of the original line, right? So find slope of original line. And I can do that because I'm given 2 points on that line. I can label them x1, y1, x2, y2, right? So the slope of the original line is going to be y2 minus y1 over x2 minus x1. So this will be -3 minus a -15 over 2 minus a -2. Okay, then just be careful with this, right? So -3 minus -15 is -3 plus 15, which is positive 12. And then 2 minus -2 is 2 plus 2, which is 4. And then that simplifies to 3, right? So the slope is 3. Okay, so now we want to find slope of the new perpendicular line. All right, so how do we do that? Well, we know, I'll call the original slope m1, right? I'll call it m1. Remember the new slope, because m2 times m1 has to equal -1, if I divide both sides by m1 here, then I know that my new slope, m2, has to be -1 over m1. So my new slope for the perpendicular line must be -1 over 3, which is just -1/3. Okay, so now for the new line, right, the one that's perpendicular, I know the slope, it's -1/3, and I know a point that it passes through. We're told in the problem that we want it to pass through the point 6, 4. So this is kind of like our x1, y1. So again, I'll just use the point slope form. So this will be y minus y1 equals m times x minus x1. So I have y minus 4 equals -1/3 x minus 6. Then typically we want our answer to be in the slope-intercept form, so I'm going to distribute in a -1/3 here. -1/3 times x is just -1/3 x. -1/3 times -6 is positive 2, right? And then if I solve for y, so I'm going to get rid of that 4, add 4 to both sides, I'm going to get y is equal to -1/3 x plus 6, I guess. And if we really want to write it in function notation, I'm just going to put f of x for y. So that would be the answer, right? That's the equation of the line that's perpendicular to that given line, which passes through the point 6, 4. Okay. Now, remember, the other way you could solve this, you don't have to use, so we ended up using the point slope form. You could also go directly to the slope intercept form. Let me just remind you how to do that. Here, I'll say or use slope intercept form directly. Okay, so what does that mean? Well, I know it's going to have the form y equals mx plus b. And I know m already. M is negative 1/3. So if I can find b, I'm done. I have my answer again. So how do I find b? Well, I can plug in this point that we're given, right? We know that this equation has to satisfy, if I plug in this point, 6, 4, it has to satisfy this equation, right? It has to make it true, because this is the equational line that's going to pass through this point. So if I plug in 4 for y, and then 6 for x, it has to satisfy this equation. But what does that allow me to do? It allows me to solve for b, right? So if I work this out, I have 4 equals negative 1/3 times 6 is going to be negative 2. And then now to solve for b, I'm going to add 2 to both sides. So I'm going to get b is equal to 6. And now I'm done, right? So the equation is y equals, the slope is negative 1/3 x, and now I know b is 6. And that's exactly what we got before, right? So you could either use the point slope form to find the equation of a line, right, with that, or you could use the slope intercept form directly, and basically what you're doing in this case is you're solving for b to figure out what b is. But either way, you'll get the correct answer. Okay, in the next section, we're going to do some applications with linear functions, like modeling with linear functions. And then after that, we'll talk about systems of linear equations. We'll remind you how to do that. Great, thank you.